continued from where we left last time, and since there is a mid-sem break, so I will not be taking up anything new. We will be just finishing analysis when T select is 0, okay, and we will just understand that. So basically today we will be devoting our time for identifying transition matrices. Rest all methods actually remain the same, and you will now also basically appreciate the difference between the two mechanisms. And of course it is possible to analyze the midway mechanisms. For example, when T select is 50% and T pass is also 50% of T delay, that kind of analysis is also possible. So I think again we require those 14 sets. So should I write it maybe for the people who are recording or who will be actually viewing the later on? So this need to be done. So these are those 14 states, okay. So now when T select, I have already given an example whereby if you do a cascading, for example, of a switch, earlier case, if all of them for example have this packet and this is the last stage or whatever it is, so they will just be deciding in the whole T delay slot, which will be happening parallelly for all the three, that where the packet has to go. Once that is done, this packet will be read out almost instantaneously, and within the same instant this packet will also be read out, this packet will also be read out, okay. But once it has come here, again it has to decide where on which port it has to go, that is why it cannot jump, but all three packets can jump together, okay. So usually that is why the T select, there were actually three phases. One is the packet going out, then packet jumping, and then packet coming in were kept separately for one particular switch, because things were happening simultaneously when the packets are being transitioning continuously, okay. So that you can do that computation. Now for our case, now when T select is going to be 0 and T pass is finite. So remember, packet can move even if the outgoing buffer is busy, it is occupied, then also packet can move subject to condition that is also moving out. So that is why you are first of all finding out whether this will move out or not, and based on that whether this will come here or not. If this comes here, then some other packet commit here or not. So there were three steps involved, and those are being iterated in one time slot. in the backward direction. So, all three transactions can happen, but now the case which we are looking is, if this is the situation, they will immediately select where it has to go. Now, this packet cannot move here unless this buffer is empty, because this whole writing itself take t delay, and this packet cannot go instantaneously out, this also will require same amount of delay, and unless this is free, this cannot start. So, first time slot this will move and you will get a packet not here. After one time slot delay, you will be in this situation. Next time slot, only this packet will move here and this packet will be read out. This will be happening parallelly. So, there is a gap, hole which gets created between the two. Okay. And this packet cannot be read because this buffer is not empty. So, after some time, when this packet will be here, this packet will be read out, this packet. So, in next time slot, third time slot, then this will be transferred here and this will be transferred here. So, that is the difference which comes when T select is 0. And T pass is nothing but T delay. So, we expect the performance to be poorer in case when T select is 0. Okay. Now, important thing, I do not require those 3 steps 1, 2, 3 and 3 will become 0 for the next time step, that is not required. I can only do with one single step. So, that is what we are going to do actually here.
To make the calculation simple or some other reason?
Where?
Chosen the 2 cases, T select 0.
Ideally it is right, none of them will be 0, they have to be finite, they have to be some intermediate value. But these are the 2 extreme situations of the performance. These are two extreme situations, so these can be analyzed simply in computational procedure. For doing, for example, 50-50, it is going to be slightly tricky, it is not that easy. Okay. Because writing into memory and reading from the memory cannot happen simultaneously. Older packet cannot be read out while a new packet is being written in, that is not possible. And they do not have a dual buffer system, the way we had in switches. See, while you are reading in a slot from one memory, you can write in the same time slot in some other memory, then you switch over the memory. That option is not implemented here. If you can implement that option, then of course, scenario will be very different. And that is technically what when I am saying T pass is 0. That is what we are indicating actually. We are having a dual buffer system technically. So, once we have decided I have within T select period or T delay period where the packet has to go, after that it does not matter. So, writing out of the packet to the outgoing buffer will not interfere with the writing in of the packet, and that can happen with dual buffer system. Okay. But notionally there is only one single buffer at per out input port with this condition. So, now the changes which will happen is you will have Pj which will be defined as it is, Pj tilde will be as it is, Pj bar will be as it is. Pj tilde was the packet will go out of your outgoing port, Pj is that packet is present at a port, okay, and Pj bar is packet is going to come into your incoming port, incoming buffer. So, these definitions remain intact. In fact, even those whatever we had the states, we had defined the state probabilities, those will also remain the same. Now, only thing which will happen is this will be the only thing which will be available. We will be only working with this because P1 will not be there, there is no step 1. Step 1 actually technically gets merged. Okay. So, only problem which is there, that P1 calculation which you had, sorry Pj, there is no P1. So, Pj tilde, Pj bar and Pj, there were 3 calculations and they required probabilities after step 1, probabilities after step 1 actually, remember P1 we were always writing. So, what will be the state probability of either j minus first stage or j plus first stage or jth stage, there were 3 actually configurations. In that case all P1s will be simply replaced by P0, because of there is no conflict. So, I am not actually having 3 steps. So, probability that after a step, after a time slot t, my packet will be going out will be decided by Pj tilde, where the probability is here, those expressions will still remain exactly same, they will not change, they will come from there. So, if you wish I can reiterate or you can just simply replace, both way actually it is fine. So, maybe for Pj tilde we can do this. Okay. So, Pj tilde, that probability that packet will go out, okay, in time slot tau k, which starts from Tk to Tk plus 1. So, at Tk this is a probability, that conditional probability that packet will go out. So, denominator you have to put all those states where you will have packet at the input. So, there will not be 1 anymore, it is P0 which will be coming. So, when the packet is there at the input port or the outgoing port, sorry, so it is half of P0, that is the only change which will happen. P2j, that is the variation which will come. I think earlier case it was, no, I think everything will remain still the same, except I have to look at j plus first stage, I have to look at all the states where the packet is there at the input, okay, j plus first, and then I have that all those states will be put in denominator. In the numerator I will put all those states where the packet will actually move out from here to here. So, that will give the conditional probability of packet going out from here. Only thing, it will become P0 instead of P1 which were there earlier, not 2, it will be actually 4 first. So, I am just putting a bracket for all halves, I will just add here. Okay. Five, this will be 6. 7. Yeah, then remaining ones actually will come. P08 j plus 1, P09, so this is what will be the denominator. Now, this identifies the probability that a packet will go out. Okay. So, I think because time slots have to be clearly specified, this is at this particular time step, just before this is you are in probability of in this state just before this particular step starts, this particular time slot starts. This is after step 0 in k minus 1, I think that is the only variation which will come. Okay. And then you find out all states where the packet will be moving out in this time slot. where the packet will be moving out in this time slot. So, this is nothing but Pj tilde is the probability that at the end of this time slot packet will go out, conditioned on if the packet is present at this point. So, I think this is the only thing which we have to define clearly, because earlier case this was not the issue, because all packets, all 3 packets can jump together, here they cannot. So, there is a minor variation in the definition here, this is not explicitly stated. So, this will basically depend on this is the probability that packet will be going out of your outgoing port or outgoing output buffer, conditioned on the packet was available at the beginning of the time slot, and packet will be going out after the time slot, or it will be actually moved out by that time, it will not be there. So, this Pj tilde is that probability. So, this is a condition on that packet is present here and packet will be moved out by this time. So, what is the probability that packet would have moved out by the end of the slot, condition on the packet was there in the beginning of the slot. So, this gives the probability that packet was there in the beginning of the time slot, and I am now choosing in the numerator only those states for which in this time slot packet will actually move out. Look at only those conditions. So, those will correspond to for example, 4, yes, packet will actually move out surely. So, you can put P04 j plus 1 k. 5 it will not be moving out, 6 it will be moving out. Eight will be moving out similarly.
Moving out from the which port, sir? Moving out from input port, sir?
Output port of jth stage and input port of j plus first stage. I am talking about j plus first stage here.
This corresponds to input port of j plus.
See, because your probability that the packet from your output is going out will depend on the
Yes, so this is the input port of j plus 1.
Input port of j plus 1, right. So, this is the j, and I am trying to estimate Pj tilde. This will be exactly same expression, I think, because in principle we had followed the same thing. Then P12 will be coming. That is it. And for
P11,
P9
P9 two path.
11, I think I have missed out something. 11 will also come, right.
Nine also.
Both will go in 9. So, I am writing 9, but this is only which is with half actually. The full ones now we will write. It is the same expression. So, full only happens for 9, I think, nothing else. Rest all or half. It must be same expression. So, in principle it is also true for Pj bar and Pj, same way. Pj will give you the probability that packet is there at your outgoing port. So, look at jth stage, find out in jth stage the switch will be in which particular state, and sum up all those probabilities. These are absolute probabilities. I am coming to that. You have to understand Pj, Pn minus 2 tilde is 1.0 in the earlier case. Now, Pj n minus 2 tilde is not 1.0, it is going to be less than that. Okay. And that will cause the impact, because now you are doing backward propagation. Ultimately, that probability what gives you the throughput. The throughput will be lower in this case intuitively. Now, the condition here is not this will be 1.0. It is not Pn minus 2, it is Pn minus 1 tilde. There at the output packet was instantaneously taken out, n minus 1 stage. So, at n minus 2 output, if there were 2 packets, both of them will also be taken out immediately, because there was instantaneous read out, but here it is not instantaneous. So, reason for this will be, now even if this is the last stage, you have a packet here pushed out, this will not be read out immediately, it takes one full slot to read out. Earlier it was instantaneous. So, only if the packet is here it will be read out. So, if there are 2 packets sitting here, for example, in earlier case both of them will be, even if they are going to the same port, they will be taken out and read out instantaneously. We kept this thing as P of n minus 2 tilde as 1. Now it is not possible. When this will go out, it will become empty, only one of them will go, other one will still be hooked up here. Earlier case even this was going out. So, this has had an impact. So, intuitively yes, the performance has to be lower than the earlier case. So, now coming to the state transition table, we will not be having state transition table after step 1, step 2 or step 3, those are not there. We have only step 0, only one step every time slot. So, in that step only all transitions can happen. Now, only change which we will have, we will still have 3 transition tables, one for the input stage, first stage of the switch, one for the output stage, because input stage Pj bar is going to be, or P0 bar is always 1.0, the way it was there in even the earlier switch, and the output stage Pn minus 2 or Pn minus 1 tilde is going to be 1. In between, your state transition depends on the incoming rate and outgoing rates both, because then it is not broken into 3 steps. So, we have to use the compound formation basically. Transition will be simpler, matrix will be simpler in this case, not complicated. So, I think in the same way we can build up for Pj bar and Pj. So, I need not probably do that, and that can be done by you. I can, if you wish, I can write down the expression directly, or earlier expressions which we had, just simply replace all P1s by P0, all 1s will be replaced by 0, that is it, the rest everything is same. So, first state transition matrix, because so we had already 3 transition matrix done earlier, so this will be identified as superscript 4, but this is for T select is equal to 0, this is for this case. So, now you have the states, and then now we can build up with this, and you have to remember that your P0 bar is 1. Okay. So, look at your state 1. In state 1, what will happen, where you will go? P0 bar is 1, remember. So, packets have to arrive. If both packets will arrive, they will be going where? You will either come to a state 8 or 9, there is no other possibility, and no 8 or 9 not. See, I am looking at a transition from this time slot to this time slot. What happens after this time slot? I am not looking into 0, 1, 2, 3 steps, I am looking at after the complete step. So, at this point, suppose you were in the state 0, state 1, both packet will arrive. So, both packet out of these T select is 0, immediately a decision will be made whether where the packets have to go. If both of them are directed to the one outgoing port, so one will be at the input and one will be at the output. So, that state will be your 5 state. Okay. If there is no conflict between them, both of them will be on the outgoing port, that state will be 3. They cannot move to the output of the next stage because it is not possible. One time slot, only one readout is possible. again there is a buffer. So, next readout will take another time slot, that will happen in the next one. Okay. So, this actually means you will have half here and half here. Okay. Now, look at the state 2. If your input switch is in state 2, both packets will come, they will select, immediately selection will be done, where they have to go. They both would like to go to the same port where the packet is already there at the output. They both may like to go to the free one, or they can do a crisscross. So, based on that you will find that, and you have to also look at what will happen in after the step 0, whether this packet will go out or not go out. See, outgoing packet also has to go out. This particular packet which is there in this state. Important thing now, even if it is being read out by the next one, you cannot write any one of these two packets in this slot. Read and write cannot happen simultaneously. So, if these two packets cannot move here, that is not possible. This can be read out or may not be read out, both are viable. So, with probability your P0 tilde this will be going out, and with Q0 tilde this will not be going out. Okay. Now, these two packets, if you look, they just come, they can be directed with equal probability to any one of these ports. So, now I have to look at iterate on the cases actually. So, let me write all cases one by one, enumerate them and then estimate the probability. So, first case is when the packet actually goes out. So, I have P0 tilde, with this will be happening. So, I will not be having any packet here. So, one possibility is both of them directs to the above side and they cannot move. So, I will end up in this state after time slot. If both of them are directed to the bottom side, I will end up in this state. If both of them are going to be in parallel, I will end up in this state. If they are crisscross, technically these two states are same, they are not different. If the packet does not go out, I will still get the same scenario. Again these two states are same, all of them are happening with equal probability. This will be happening with 1 by 4 P0 tilde, this is happening 1 by 4 Q0 tilde for all 4 of them. So, let us identify, this one is which particular state? 8. Okay. This one is 5. This one will be 6, both of them.
Can you explain how the 6th step comes? Step 6, when both packets come. Is it a parallel?
What?
In case 1, when packet move out, how do you reach the state 5 after it? First case.
First case, this one.
After that, packet move out from output port, 2 packet arrive and then
2 packet arrive, they cannot be written into this buffer.
that's true.
They both are directed to this. So after the, see, this is the time which is starting. You started at this point, 2 packets arrive, okay, in the incoming port. Now at this point the packet is being read out from the outgoing port. At the end of this time slot, what will happen? This packet is no more there in this buffer, but these 2 packets cannot be moved because they both were directed to that particular thing. So this decision was done instantaneously, T select is 0. So both of them have to remain here and they are still directed towards that direction. So this scenario look from that table is stated.
Next 5 you are
This one, okay. So if the packet is again going out, so next one is when both of them are directed towards downward actually. When both of them are directed towards, this case comes when both of them are directed towards downward state. So this was the situation at T, at this point. By this time you reach here, this one packet will be pushed here. See, this is before, at this time what will happen? This packet will go out and this packet will move from here to here. You will end up in this situation. Okay, maybe I can write it in a slide. I will use a different color and show what is the situation at this time, and this is a situation at this time actually, okay. So just before the start of slot, I am drawing with that different color. So just before the start of the slot, this is a situation just before the start of the slot in this case. So if the packet does not go out, you will end up here, packet goes out, you will end up here, output port packet. In this scenario, this is at the beginning of the slot which is happening. If the packet goes out, packet is no more here, one of these packets will be coming on this side. One of these packets will be coming on this side actually, because this output buffer is empty. This read out can happen in this slot. So if the packet is not going out, you are here, otherwise you are here. The initial thing in this scenario will be this, or this. If the packet moves out, you come here, this packet goes out, this remains there, this one will move on the outgoing side. If packet does not move out, this still goes to the outgoing port, comes here, this will remain blocked and this will remain as it is intact there. Two situations. Same here. I think this clarifies. So this is at T k, and this situation is T k plus 1. And then of course whatever are the stages which you arrive after in time slot tau k, I just give them the numbers and based on that I will fill up the matrix. So this one is 6, this one is 5, 8, this is 10, 7, this is also 7, and this is also 7. So 7th I can write here, three by 4 q0 tilde, 10 I can write 1 by 4 q0 tilde, 8 I can write 1 by 4 p0 tilde, 5 is also 1 by 4 p0 tilde, 6 I can write as half of p0 tilde. Fine.
7 states 2 dash comes 3 times.
7 comes 3 times, 3 by 4 Q0 tilde. This row happens with probability P0 tilde, packet goes out, Q0 tilde, packet does not go out. P0, Q0 tildes depend on the next states of the next state. So, only thing important is packets are coming immediately into the port the moment those are free. So, I am assuming there are infinite buffer here, packet is always there present. So, it is not that when you read out this packet, so no other packet can be written in the same time slot, it will be instantaneously written in the input port. Well, that is the only variation which you have to be careful about.
Single buffer is possible. Why we are taking infinite buffer, not only single buffer?
Where?
Input port we are changing.
No, all switches have input single buffer per input port. I am talking about the complete switch at the input of the 0th stage. So, there I say if the packet goes out in the next time slot, instantaneously another packet is available. See what happens is you have a packet here, it takes hold one slot for this to be read out. What happens the next one? You cannot write the packet instantaneously in this buffer, usually it should remain vacant for the next one. No, that is not the case. I am always assuming that P0 bar is always 1. So, 0th stage the packet will be always there in every stage. So, even if the packet is read out takes whole time, next slot the packet will be immediately available. So, that is the maximal loading condition. Now, staggering of the packets or they are being stopped because they cannot be read out is happening inside the switch. I am not looking at the input. So, input technically if there is a large switch with multiple stages 0, 1, 2, 2, some whatever it is n minus 1, at this input I am assuming it is like a large number of packets are there. So, at least 2-3 buffers must be there at least always, and they are always present. While this does not happen inside, so that is the reason why you could not have, when this packet was going out you cannot move a packet here because there was only one single buffer here, but at the input of the whole switch packet is always available, which actually means there is not single buffer, there is going to be more than one buffer present there. That is a thing, otherwise I cannot take this case, and that is the condition for maximal loading. We are trying to compare. So, there has to be equal testing ground for the both kind of models. So, remaining ones I am just writing it down by looking from the paper for this particular matrix. Okay, we do not have much time. So, this Pj tilde square Pj tilde square maybe you can actually look into the paper and get the whole table, I need not write it down. Important thing is that how to get the table. Now, you can even drive on your own also. So, let me just quickly go through the middle stage what happens. There is now arrival and departure probabilities, both are there.
This will be J, sir. We are talking about input stage 0.
This will become 0, J is equal to 0. They actually have given it in general form. Again you will have the equation, I think this I can now remove. Okay, this is for a state I, how you will compute. Time step k plus 1, this will be nothing but your transition matrix which will be there, m is equal to 1 to 14, P0 m 0th stage whatever was in k so this will be happening for all i's. So I goes from 1 to 14 in all case. So this will be transition matrix can be the very similar thing what we did earlier. Now let me define this thing as T0 Tj5 we call it, not T0, and we have Tn minus 1 6. So this for jth stage in general, not for 0th stage. 0th stage case is different because the input probability is this, but now there is an input probability Pj bar and Pj tilde both are have to take part. So first one you take, for example you are in state 1, I am only looking at this, okay. So what will happen? Only packets can arrive, packets cannot go. So packet will arrive with probability Pj bar. If both the packets will come, it is a Pj bar square which will happen, and then you will end up in a state of 8 and 9. 8 and 9, that is what will happen. So you will have half Pj bar square, half Pj bar square here. If none of the packets come, you end up in same state. Oh sorry, upper line also need to be removed, this should have been here. Qj bar square, and of course only if only one packet will come, then you will be in state 4. Pj bar, Qj bar. Okay. And so on. Next one, if you want to build similarly, what will happen if you are in a step? So now you have to look at the arrival as well as departure, both probabilities together. So you are in the beginning of time, beginning of talk A, you are in step, this particular step. No packets, there is only one packet. This is the state to begin with. Now you can actually have your initial state. Basically what will happen after your, you started at this time, what will happen? Packets can arrive, but they are not instantaneous arrival the way it was happening in the first stage. First stage was, or the 0th stage. Here packets can come or packets may not come, and this can go out independently. Okay. Only if packet is already available, it will move here, if that slot is available. But when packet is being pushed in, this will take this much time, and packet will be available only at this point, at the input, in the input buffer. So they cannot be moved to the outgoing port. So with this, now the possibilities are, this is, remember, with Qj tilde, you will have no packet here with Pj tilde from state 2. So I have written those two, and depending on the situation, this will be now correspond to Qj bar square. You can have a packet Pj bar, Qj bar, okay, directed to this half probability. Remember, this only one packet coming in can happen with 2 Pj bar, Qj bar actually. Half of it will be directed here, half of the time it can be directed here. These two are different cases. So only one packet arriving, and this can be directed to any one of them with equal probability. So remaining half will come here. So I have to multiply this by this actually to write in the matrix. And next possibility, that 2 packets will come. This still remains, the 2 packet will come. This is Pj bar square. Now with they can be directed here. So this probability is 1 by 4. they both are directed to the bottom side, this 1/4, and then of course there is a case so this can be crisscross also, it will be 1/2 actually, Pj square bar. So equivalent things you have to write with Pj tilde, this with Qj tilde. So you can then identify the states and then build up the row. So I can just quickly write what you will get is Qj tilde, no packet, okay, Pj square होना चाहिए, Qj. Okay, bar part I will always write first. No packet arrives, Qj square, Pj tilde. There are two different things which I am multiplying, I will remain in the same state. I will end up in this state, no packet arriving. Okay. You can similarly build up only one arriving, going to a free port, Pj bar, Qj bar, Pj tilde.
First state will be sir. First state. First state is Pj square, Pj bar tilde square, Qj bar square.
Sorry, this will be Qj. Same thing will come, sorry. The same expressions will come here except the outgoing packet will not be there. That is the only difference. So you will be in state 2 with, okay, let me just identify those states which I am doing. That is state 4. This also I need to include. These two are technically same states. Here they are not same states, there they are same states actually, when the packet is going out. So I have to multiply it by 2. So this is fourth state, it will be 2 Pj bar, Qj bar, Pj tilde. So this is an example. So I think you can build up in this fashion for this particular row. So again you can look into the paper. Important thing that you appreciate the method, that now both incoming probabilities and outgoing probabilities have to be considered while building up the transition matrix. It is not like the earlier cases. So I am actually stopping here. The last one is for the outgoing port, or the what we call n minus first stage outgoing ports based on that. Okay. So remember, the packet will certainly be going out. Your P n minus 1 tilde is always 1. Only the arrival probabilities will be participating. Remember, when I did for the input stage or the first 0th stage, there was only outgoing probabilities which are participating. In intermediate stages, both of these will be participating. On the outgoing, on the last one, n minus first stage, only incoming probabilities will be participating. Outgoing is 1.0 defined there. So in the very same fashion, actually we can do that, and we will define that thing by 6 n stages n minus 1. Okay. So same fashion actually you can build. See, for example, you take state 2, because there is a packet on the outgoing side. I am taking only that example. This packet will certainly go out. You cannot stop it, it is 1.0. So once it is 1.0, so only the packet which can come at the input, that is important. So no packet comes, it is Qj square, Qn minus 1 bar square. So you will come here as Qn minus 1 bar square. You will remain in the same state, outgoing port will go. if you are in state 3 for example, both packets at the output port will certainly go out. Okay, you will come to state 1 from 3 if no packet comes in same fashion. Okay, if for example both packets will come, then 2 will turn into either 10 or 9 for example. If both packets will come, you will either become 10 or you will become 9, one of the two, depending on how the packets are being directed. So, you can have to have half for p n minus 1 bar square
Both packets come.
both packets are arriving.
Yes, sir.
So, this arrival happens with p n minus 1 bar square probability. Outgoing packets does not matter, they will anyway will be removed, that probability is 1.
Good. So in that case it will go to 8 no sir.
So, if both of them are here, they both can go to the same port or they both can be directed to separate ports. So, if they go to the separate ports, it is 9.
9.
Sorry, 8 and 9, 8 and 9, you are right. This has to be written at 9. Yeah, that was not visible from here. Here. In fact, if you are carefully observant enough, you can just simply put in that Tj5 case your outgoing probability equal to 1 and you will get the same matrix actually. So, the middle one or T's J5 is what is important. From that you can actually get the first one as well as the last one. Only thing you need to know the boundary conditions. Okay. So, if you just apply the boundary conditions, you will get even this particular matrix. Now, remaining procedure remains the same.
What will happen in case of 13 and 14?
13, 14, these packets will go out, that is it. It will remain here. So, 13 to you will come to 8. Yeah. There is no other option. If you are in n minus first stage, this both will be read out, these packet cannot move here. So, you will come up with 8. If you are 14, you will come to 9. So, I think that gives more or less the idea of that how even this analysis is done when T select is 0. So, after the midsem break again we will continue with and I will start with some fresh topics. So, this buffer delta finishes off at this point.